This video is part of an online course of multivariable calculus, and I'm going to talk about conservative vector fields and how to say that a vector field is conservative and how to find its potential function. Okay, so let's say f, which is pi plus qj, is a vector field, and let me write this in the vector notation. And then we say that f is conservative if f is equal to gradient of a function f for some function f. Okay, so what is gradient of a function? Gradient of a function is equal to partial derivative of the function with respect to x and partial derivative with respect to y. Okay, so the vector field is equal to fx and fy. So I'm gonna move this one into here. If the vector field f is conservative, we have this equality. So I can say that the first coordinate in here is equal to fx, and then the second coordinate q is equal to fy. Also, we know that f of xy is equal to f of yx. Partial derivative of f with respect to x and then y is equal to partial derivative of f with respect to y and then x. Okay, so now let's take derivative of this equation in here with respect to y. So py is equal to fx and then y. How about in here on the second equation, q is equal to fy, I'm going to take derivative of that with respect to x. So I get q with respect to x is equal to fy with respect to x. Since these two are equal to each other, then I can say that p with respect to y is equal to q with respect to x. That's the criteria that we need to check. Okay, so it's actually a theorem. And the theorem says that a vector field f with coordinates p and q, where p and q are basically functions of x and y. Okay, so let me write it in here. P and q are functions of x and y. Then the vector field f is conservative if and only if p with respect to y is equal to q with respect to x throughout the whole domain f. There are two actually things that we need to check for this theorem to make it complete, but we are not going to use a lot for the course. And these two properties is that, one, the vector field f needs to be defined on the whole plane R2 or on a simply connected region. Simply connected region D. What do I mean by simply connected region? This definition, it means that it's a region without any hole in it. Without any holes in it. Which means that it is a region like this. It's like a simply connected region, and this region that I have in here that has a hole in it, it's not simply connected. Not simply connected. And the second criteria is that p and q, these two coordinates of the vector field, should be continuously differentiable. Are continuously differentiable, which means what? Which means that p and q have continuous first order order derivatives. Okay, so let's look at an example to see how we can apply this theorem and figure out that our vector field is conservative or not. The example is this. Let the vector field f to be 3x squared plus 8xy I plus 4x squared plus 3y squared j. Check if it is conservative and find the potential function f. The potential function f. To check that it's conservative, we need to say that this is the first coordinate, this is p, this is the second coordinate, which is q. I need to say that p, derivative of p with respect to y should be equal to derivative of q with respect to x. Okay, so let's do it. So p with respect to y should be equal to q with respect to x. What is derivative of p with respect to y? This is 0, and derivative of this with respect to y is 8y and 8x actually. Derivative with respect to y is that, and then q with respect to x, this part would be 0 because y would be constant, and derivative of that with respect to x is 8x. So as you see, since these two are equal to each other, then f is conservative. Now for the second part, I need to find the potential function f. Okay, so what is the potential function? The potential function is the function such that our conservative vector field is gradient of the potential function, and so p and q is equal to fx and then fy. So we need to find a function f such that p is equal to f of x and q is equal to partial derivative of f with respect to y. So I need to find a function such that derivative of that with respect to x is equal to 3x squared plus 8xy, 3x squared plus 8xy, and then derivative of that with respect to y is equal to 4x squared plus 3y squared. Okay, so how do I do that? I'm gonna say that I'm gonna let this equation here to be 1, this equation here to be 2. Okay, so based off 1, fx is 3x squared plus 8xy. I'm gonna take the integral of that with respect to x from both sides. So the integral of partial derivative with respect to x dx and the integral of 3x squared plus 8xy with respect to x. This is derivative. Now, this is antiderivative of the function with respect to x. So I have the function itself as the answer for this integral in here. And then the integral of that with respect to x is equal to what? This is x cubed. And then y and 8, both of them are constant. So I have 8y. The integral of x is x squared divided by 2. So on here, if I simplify that, I get 4x squared y. Now, plus a constant c, but the constant c in here is actually not just a constant, it is a function of y. Why is that? Because the integration constant is independent of x, but it could be depending on y. Because what? Because if I take derivative of that with respect to x, this part would be 0, and then I get the integrand, as you see. So let me write this one in here. The integration constant c is independent of x, but still can depend on y. That's why I write it g of y. So I have the function, the potential function has this equation, but I need to figure out g of y. How do I do that? I'm gonna use the second equation in here. By the second equation, I have what? I have partial derivative of f with respect to y is equal to that. F is this. Let me take the partial derivative of that with respect to y. Is equal to what? Derivative of that with respect to y is 0. Derivative of that with respect to y is 4x squared. Derivative of this with respect to y is g prime of y. And based on equation 2, partial derivative with respect to y should be equal to this. So let me set it equal to that. Very good. Now, this and that would be cancelled. That's why g prime of y is equal to 3y squared. It's nice, it's just because you said that derivative of the function that is depending only on y is equal to that. That's how you can check your work and make sure that your work is correct. So now what I'm gonna do, I'm gonna take the integral of this with respect to y. I have what? I have the integral of g prime of y dy is equal to integral of 3y squared dy. The answer for this part, the antiderivative of the function g would be the function g itself, and the integral here would be y cubed plus the constant c. Now this constant is a true constant, it's not a function of anything. Now c here is a true constant, just a number. Okay, very good. So let me summarize what we get. F of x and y is equal to x squared plus 4xy squared, 4x squared y, x cubed plus 4x squared y plus g of y, and we found g of y is equal to this. So plus y cubed plus c. That's the potential function for this conservative vector field. That's how you should find the potential function. You need to set the first coordinate equals to fx, the second coordinate equals to fy. Starting at fx, take the integral of that. So this is the crucial step. And then you write equation, you write the integration constant as a function of y. Then we are taking the derivative of that with respect to y. So this is another step. We find g of y, and then we just put everything together. That's how we can find the potential function. Now I'm gonna make a small note, and is that not all vector fields are conservative. Look at this vector field. F negative yi plus xj. So in the vector notation, it would be negative y and then x. Okay, I'm gonna take the integral of that over a closed unit circle. X-axis, y-axis, it's 1, counterclockwise, C. Okay, I'm gonna find f dot dr over c. Okay, so let me parameterize the curve c. X of t is just because it's a unit circle, cosine t, the second parameter sine t, and then t from 0 to 2 pi. Okay, so r of t is cosine t and sine t. Derivative of that is negative sine t and cosine t. Okay, so I'm gonna put the parameterization into the vector field, which is what? Negative y is sine t, and then x is cosine t, and then r prime of t, which is that negative sine t and cosine t dt. I forgot to put dt in here, and then t is from 0 to 2 pi. Okay, I have a dot product in here, so negative sine t together would be sine squared t, and then cosine t plus cosine t, it would be cosine square t dt. So it is 0 to 2 pi. Sine square plus cosine square is 1 dt. So the answer would be t from 0 to 2 pi, it's 2 pi. If this vector field were conservative, then the integral of that over a closed curve C should be 0, but it is not 0. That's why F is not conservative. By the criteria that we just discussed, let's check. P with respect to y should be equal to Q with respect to x. What is P with respect to y? P is this one. The first coordinate, we call it P. The second coordinate, we call it Q. P with respect to y is negative 1. Q with respect to x is 1. Since negative 1 and 1, they are not equal to each other, so the vector field is not conservative. Okay, so not all the vector fields are conservative. Only those who has this criteria, they are conservative, and you can find the potential functions for them. That's it.